let's start with some easy examples where you can determine the limit of a function algebraically. Here's an example. Limit x going to 2 of x squared minus 2x minus 8 over 3x minus 6. By determining limits algebraically, I mean changing an expression into another equivalent expression, and then when that equivalent expression is easier to compute, then you evaluate that limit. That's what I mean. So here, I can factor this as x plus 4, x minus 2. Okay? 4 plus negative 2 is positive 2. 4 times negative 2 is negative 8. So it is true that the top can be factored in this form. Whereas in the bottom is 3 times x minus 2. As you can see here, both top and bottom has x minus 2, which I can cancel. So I've managed to change this expression into an equivalent expression, which is x plus over 3. Now, what's the difference between this function and that function? We discussed this last time, that although these are equivalent expressions, here you're not allowed to plug in 2. Why? Because the denominator becomes 0 if you plug in 2. 2 times 3 is 6. 6 minus 6 becomes 0. So you're not allowed to plug in 2 in this expression. However, here you are indeed allowed to plug in 2 because you just have 3 in the denominator. So then let's do that. Now let's just plug in 2. 2 plus 4 over 3 is 6 over 3, which is 2. If you used a calculator to plug in numbers that are very close to 2, say 2.1, 2.001, 2.0001, then eventually you will see that the value you get is very close to 2. So that's what I mean when I say you should, when I say evaluating limits algebraically. Let me show you a harder example, example 2. What if I had x going to 0 of let's see, this is what. So the easiest examples are the ones where you can just factor and that's it. But there are other harder examples where you have to know what to do. So for example, if you have a square root, one of the things that you do is you multiply the conjugate of this expression, top and bottom. So that's one thing to just know. Okay? Whenever you see a square root on either top or the bottom with another term, what you do is you multiply the conjugate of that expression, top and bottom. So you're going to multiply the square root of x plus 1 plus 1, top and bottom. And here we are using the principle that if you have a fraction and you're multiplying something on the top and you're multiplying the same thing on the bottom, you haven't changed anything, because you can always go back to the previous one by canceling what you multiply. So if you cancel these two, you go back to the same thing, right? So although this looks much more complicated than the previous one, these are in fact exactly the same equivalent algebraic expressions. In other words, any value you plug in here and any value you plug in here, they evaluate to the same number. Okay? So they're perfectly equivalent. Now, why do we want to use the conjugate? The reason that we multiply the conjugate is because we want to use the following formula. A minus b times a plus b gives you the difference of squares. Probably seen this before. So if I multiply a minus b and a plus b, I will get the square of the first one. Square root of x plus 1 is the first one, and you square this, and you subtract by the square of the second one. So you get this. And then they cancel, that's 1. So you end up with just an x. And we are almost there, because now you can get rid of the x's, and you essentially have 1 over square root of x plus 1 plus 1, and there's no problem in plugging in 0 to this new expression. So here, we couldn't plug in 0 because we had 0 in the denominator, but here, if you plug in 0, you don't get a 0. You get something else, right? So if you plug in 0, you get 1 on the top. You get 1 because x is canceled out. You should really think of this as x times 1. After x is gone, you have 1 left. And if you plug in 0 here, you get square root of 1 plus 1. But what's that? That's just 1/2.